Hey, what's up, guys? Chung here. This time, let's continue our LeetCode journey. Number 774. Minimize max distance to gas stations. All right. Okay, let's take a look. You're given like stations uh, of gas stations and the number K here, and you need to return the minimum distance, the minimum of the minimum distance between all the gas stations, right? After you after adding after adding case stations to this array here. So the minimum of the max distance between gas stations. So basically, let's say there are like 10 ways of adding case more gas stations into this array, right? For each of the scenarios, you will have like a maximum distance between the gas stations, right? And among those 10 different max gas stations, you need to return the minimum of from them. Okay, and since we are like dividing, right? Since we are keep adding distance, so the one, let's say if the distance from station one to station two is one, let's say there's one and two. If you add one more, if you add one more stations right in between them, right? It's gonna be let's say there's a like S3 in here, right? Then the minimum station will become the minimum distance will become 0 0.5, right? If you keep adding another one right in between them, it's gonna be a 0 0.25 and then 1.5 and so on and so forth. It'll be like keep decreasing until a very small number. That's why it says number 4 here. Answer within 10 to the minus to the power of minus of 6 of the true value will be accepted as correct. And so for this problem, as you guys can see here, so this is another like problem to get the the minimum of maximum, right? So when you see this getting from the minimum of maximum, usually there are like two ways of solving the problem. The first one would be like dynamic programming, which will be like the time complexity will be the n square times m, where n is the number of the station, and m will be the k here. That's the dynamic solutions. And the second one will be the binary search, right? The binary search will be like n log log what? Log sum, the log of the upper bound basically, right? And binary search will be much faster. So this time let's try to solve this problem by using a binary search, right? Okay, so for binary search, right? So binary search we need a lower bound and upper bound, right? So left and right, right? So I usually use left and right here. So left obviously will be 0 because that's the distance, right? The distance, the minimum distance for it's gonna be ideally, right? Basically, there's no distance here, but we just use 0 as a lower bound. How about upper bound? So the upper bound will be mm, so the upper bound will be the last. We can either use like 10 to the power of 8, or we can just use let's just use this. Yeah, we can either use 10 to the power of 8 because that's the ranging station, or we can use what? We can just use the last station uh, position minus the first stations, right? That's gonna be the upper bound, right? So what do we do here, right? We just do a while, right? So, but in this case, remember, so we're trying to get close to the answer, right? Basically, which means because before we can just do a left less than equals to right, and then we just do this, right? That's the normal like uh, binary search. But in this case, right, since the difference could be very subtle, right? It could be way less than one, right? So in this case, basically the left and right, they may never be the same, right? We're just trying to get close to the real answer in this case. So in this case, we're gonna do what? In this case, right minus left. It's less than, right? As long as it's less than this range here, then we know we already find the answer, right? That was the answer. It's gonna be 1e minus 6, right? That's the final answer here. Middle, right? Same thing, middle here. Right, left plus right. Sorry, divided by 2, right? And since we're dealing with like the double types here, we will not be doing like a double slash here, only the one single slash. And then what? And then we just do a possible. We do a check here, right? I'm gonna define like helper functions here to check if it is possible, right? Possible, right? Of the distance. So what does this function check, right? It checks with current distance. If it's a current distance, if it is possible, we can use not we can use at most. So I mean with the current distance, if we can use uh if we can insert no greater than k stations, right? So that each station will have at most the distance here at this distance, right? If that's the case, right? If that's the case, what does it mean? It means that, okay, let me finish this. It means that we can this answer, right? This answer satisfied our conditions here, which means we can continue to decrease this distance because we want to check the minimum, right? The minimum of them. Because which means this with this distance, it can satisfy this k conditions here. That's why we will be try to decrease that. Otherwise, right? Otherwise, if we cannot we just do a if it cannot means if you will be using more than k stations to satisfy this distance, that means okay we need to increase this distance a bit, right? So that we can use less k. Okay, so here is the tricky part here. Okay, remember, usually if we have this thing here, okay, we know, okay, it satisfies the conditions here. That's why we do a mid to right because we know, okay, so this right might be our result, right? That's why we do a close here. But when we do a left here, we usually do a mid plus one, right? But in this case, we can't, right? Since the mid and the since the mid and the next answer may be way less than one because the type is double, so that's why we cannot do a minus one here. We have to use a middle here. If we do a minus plus one, maybe the answer is somewhere between the middle and one, right? Then we'll be missing that answer. So that's why we can only use the middle here. And if we use the middle here, and since we are uh, doing this kind of check here, it's guaranteeing that we will be close to our answer, and we will not be having this infinite loop because the left and the right they're both like double size, and so that and here we're also using like this single slash here, so there won't be an infinite loop here. It's every time we'll get like a different number right in between the left and the right, right? So that's that. Okay, so now let's implement this possible, right? With the distance here, how many stations we need to add, right? Gas, new gas station, gas to add. How about this, right? So, and we return, right? The stations to add, uh, it's not, it's not greater or it's not greater than k, right? And then we know, okay, with this distance, it's possible that we can only, it's possible to satisfy this case condition, right? Then how do we calculate stations to add, right? We simply do a loop, right? Basically, we loop each of the stations in the station, right? For, right? I in range, and we compare the current station with the previous one, right? Length, the stations minus one, right? Since we're going to compare, uh, I mean, either one is fine. The current one, the next one with the current one, or the other way around, right? And so what's gonna be the new stations here, right? Let's take a look here, right? Let's say we're gonna do like, sorry, the stations. So basically we're doing a stations, the next station minus the current station. We're trying to get the distance, right? The distance between the next station and the current station. And to be able to get the maximum distance of this distance, right? So how many stations we need to add between those, right? How can we calculate that? Okay, so let's think about this, right? So let's think the station I plus one, its position, let's say is 3.4, okay? And the I, how about the I? Let's say the position is 1, and the distance is also 1, and distance is also 1, right? So now what's the current distance between I plus 1 and I is 2.4, right? It's 2.4. And our goal is that the distance cannot be greater than this one. Then how many from this to this, how many stations we need to add in between here so that the distance will be smaller than 1? How, right? So in this case, we can see which we need to add the difference, 2.4 divided divided by the distance, and then we do a floor. Basically, that's the stations we need to add in order to make the distance from I plus 1 to I is smaller, it's not greater than the distance. See? So if we add one more station right in between here, right? Let's say there's a one station here. What's the distance now? Uh, 2.4. So uh 2.2, right? So this position will have 2.2. And after adding this one, right? After adding this one, so the distance between all those three stations will from 2.4 to 1.2, right? And but this one's still greater than 1, right? Let's try to add another one. let's if we add another one, we amortize it, right? So like if there are like two stations here, right? Two stations right in between, right? Then each station's distance will be like 2.4 divided by 3, right? So in this case, it's going to be 0.8 in this case, right? Then 0.8 is smaller than 1, then yeah, then we just need two stations to be able to make the distance from this I plus 1 to I less than 0, less than 1, right? Another example, let's say the I plus 1 and I. Let's take another example here. In this case, this example shows you the scenario that the distance greater than distance, right? How about the ones if the distance between the I plus 1 and the I, they are already smaller than distance, right? Then if that's the case, this this value here, right? This value here will be smaller than distance here, right? And then this division will give us 0, right? This floor 0 point something, right? 0.1234 will give us the 0.0 point a value because this is smaller than that, and the floor will give us 0, which means it will not it requires 0 station to be added in between, right? Okay, cool. So let's come back here. So now since we have that, right, let's finish this calculations here, right? So every time when we every time we get the distance between two adjacent stations, we just do like what we just saw discussed. We do a floor, right, of this thing and divide it by the distance, right? In the end, we just return, okay, so if this station to add is not greater than k, then this is possible. And if it is possible, we know, okay, we might already find the answer, right? But this maybe this this middle here may not be small enough, right? That's why we need to keep moving to the left. And in the end, we simply, oops, sorry. In the end, we just simply return either left or right and right. And let's in this case, let's just return right. Okay. And that should do it. Oops. Oops. Uh, let's see. What did we do wrong here? Mm. Do we need to return left here? Probably not. No. Oh, I think I found out what's wrong here. So here is to be greater than this one because once the difference between left and right is smaller than this this range, this like delta here, and then we know we find the answer, we can just stop. Otherwise, as long as this one, the difference is bigger than this one, we know we have to keep looking at it, keep shrinking the range here, right? And I think that should station stations, okay, yeah. Let's try to execute this thing. Cool, passed. All right, very cool. So it's basically it's using the similar idea of some other problems to get the minimum value of the maximum, right? Basically, we simply try to do a search. We search to the answer directly, right? The answer just will be whatever it needs us to calculate, right? In this case, it's going to be the minimum distance. The minimum distance, right? Then we simply just do a range of this distance from the left to right, right? And then every time with the current distance, we need to come up with a condition here, right? So that we know we can either search on the left side or right side, right? In this case, the condition is with the current distance here, can we use less, not more than case distance, case new stations, so that all the stations will have no greater than distance, right? If that's the case, we know, okay, the current one works, but is this one the smallest? Probably not, right? So that's why we need to keep going to the left. That's why we abandon the right half and then we go to the left. Otherwise, we know, okay, this distance is too small, which will give us more, which means we will add more. We need to add more k, uh, add more stations than k to satisfy these conditions here. That's why we need to move it to the right side, right? But remember here, since we're like I said, since we're dealing with like a very small double type integers, we cannot do a plus one here, right? That's why in here we do a divide, not like double divide, right? We simply do a divide here. And then when we close to this, falls into this range, and then we know we found the answer. All right, cool guys. I hope you guys enjoyed this video, and thank you so much for watching the video, and I'll be seeing you guys soon. Bye bye.